Yes, yes.
You are working on, I always get you're working on the eclipse, solar eclipse thing, or am I confusing you with somebody else?
You're confusing.
That's Father Tim.
Else.
That's Father Tim. Too many fathers. You are all from a part of the Faith Astronomy workshop, and I just, so I got to start with the story. We celebrated Thanksgiving here in Rome. All the American Jesuits met up, had mass at the Jesuit headquarters, walked off to a fancy Italian restaurant, had 2 plates of wonderful Italian pasta, and then they came out with bits of turkey and pureed potatoes. They do not understand the difference between pureed potatoes and mashed potatoes, but nonetheless. And I'm sitting chatting, and there's a Jesuit about my age, maybe a little bit younger, sitting next to me. And he's going on, and we mentioned some Jesuit, in common. He says, "Oh, I knew him in Ann Arbor." And I figure, oh, this guy had been in Ann Arbor. I wonder if he knows my old friend from my philosophy days, a guy named Joe Wagner, who had actually discovered 4 asteroids when he was doing a Europe project at MIT many years ago. So I turned to him and I said, "Do you have any news from Joe Wagner?" Wait a minute. "You're Joe Wagner." And he looks at me and he goes, "Yeah." It had been a few years. I didn't recognize him. I was about to ask him news about himself. So it goes.
We
We're all
are
getting a little bit older, a
guys.
little bit grayer. So it's now 6:02 my time, noon 02 in the East Coast. Let's go around and find out where people are and what they're up to. Joel.
Thank you, brother. I'm in Green Valley, 30 miles south of Tucson. Weather is a little overcast. It's been coolish for the last few days. Not too good of scope viewing, although I'm eager to get back and doing some stuff, but very nice.
Larry.
I'm Larry Lebofsky. I'm north of Green Valley, north of downtown Tucson. I think it's supposed to get to 72 or 73. My background is Mount Graham, which I am supposed to be literally on my way right now, but personal circumstances have kept me home, which is good because I think there's snow up there, but we won't go there.
Okay, Francis.
Hi, greetings from Davenport, Iowa. We just had our first snowfall, about 3 inches. Today is sunny and -6 Celsius.
Okay. Joe Stickney.
You're muted, Joe.
Okay, yeah, Deacon Joe Stickney from Phoenix, Arizona. It's cloudy here too. I'm an amateur astronomer, just moved into a retirement home called Beatitudes, and I'm teaching an astronomy course, we have about 25 people there. I'm having fun making the PowerPoints. I helped Jim Wren and Pam Snyder with a couple talks to the Franciscans and the Jesuit parishes.
Fabulous. Dennis
McCarthy in Denver, Colorado, where it's clear skies and temperature right at freezing.
Okay. Carmen in Uruguay.
Yes, I am in Uruguay, Montevideo. I am a lawyer. I belong to the Dark and Quiet Skies group, the Policy Hub, and we are basically dealing with the impact of satellite constellations on astronomical observations, but also on the free access to sky for everybody. Thank you.
What's the weather like there right now?
Yeah, 31 centigrades. We
Okay.
can go to swim to the beach.
Wonderful. Fernando.
Yeah, hello. And good evening from Munich, Germany. It's about 0 degrees here. Winter is definitely coming, and it's already dark since a couple of hours ago.
Okay, Chris Kennedy.
Mystic, Connecticut, sunny, 50 degrees, and being the development director for the foundation, just a small plug for tomorrow being Giving Tuesday.
Absolutely. Pamela.
Morning, or good morning from me to you in the evening in some places. I'm in Glendale, Arizona. The weather is overcast, as Deacon Joe Stickney just said. He's in nearby Phoenix. And I'm working with Brother Guy on a poster project.
Excellent. Glad to hear that's going forward. James, Reverend James.
I am calling from Woodbury, Connecticut. That's about 2 hours from Mystic. It's about 48 degrees Fahrenheit and a little bit after midday.
Okay, Gary.
Hey, I'm in Milwaukee, Wisconsin, and we also just had our first snow of the season. And so it's 22 degrees here.
Okay, Richard.
Here in Corpus Christi, Texas. I'm an engineer and I'm getting in trouble again.
Up. You're not muted, but we can just barely hear you.
Oh, okay. Richard Sam, 54 degrees, Corpus Christi, Texas. And I'm getting in trouble again. I'm disputing the Pioneer 1011 deceleration.
Okay.
Okay, thank you.
Okay. Alfred.
I'm Alfred Crocker, a southern suburb of Minneapolis, and sun is out, but 14 degrees Fahrenheit, which is 10 degrees below 0 Celsius. Coldest day of the season yet.
All right, great. Yeah, I guess you're bilingual when it comes to temperatures. So most of us can't do that calculation in our head. Lucy.
Hi, Lucy Rogers in the UK, where it's currently about 3 degrees C and been raining all day. New to this group and an amateur astronomer.
Great. And Jill. So you're unmuted, but I don't hear you. Jill? I guess the microphone isn't working. I know normally you're in Connecticut, and I'm sorry I missed you with your group when you came through here to look at the artwork. Okay, and it just says yes. So I guess I'm in Connecticut. Fine. I'm here in Rome where it's 6 in the evening, and it's been in the 40s of, in Fahrenheit, which is just below 10 Celsius. And it's been kind of cloudy for the last couple of days and rainy today. So definitely the winter has started, and it may be a few months before I see stars again. Great to connect up with all of you. I just got an email from Paul Gabor, who's normally gives us the update on what's happening at the telescope. He's big in a yet another committee meeting. That's why I made him the vice director, so he can go to committee meetings and I don't have to. But the telescope has been behaving itself. I do get the regular reports. We had about a week of use with Richard Boyle, and he was up on the telescope with people from Galway who are trying out the newest version of the Galway ultra-fast imager, or the Goofy camera, and they were looking at planets of all things. They had a session where they spent a couple of days looking at Jupiter at a very high refresh rate, hoping to see maybe a flash of light from an impact. And these apparently impacts occur often enough that there is a reasonable chance they would have seen one. I haven't heard if they actually have yet or not. He was followed by Jean-Baptiste Kekwaya. Normally when Jean-Baptiste goes up, that means the clouds come in. He has had, over the last few years, terrible luck, but he had great luck this time and got several good nights of observing asteroid positions. After him came a team from northern Arizona, and sadly, they're the ones who were caught up in the clouds. So they've been, testing the equipment, but they really didn't get any new information. And Larry, you can tell us about the project you're not doing right now.
Right, the mic icon is hidden, so it's not easy to get to. In theory, I'm literally driving now to Mount Graham, except I'm not. My two associates are, and we have a project for doing follow-up observations of near-Earth asteroids, ones that have the potential of hitting the Earth. And we have found a niche, which is basically observe when nobody else dares observe
during the full moon.
Full moon, which is why we're on our way to the telescope now. So we observe usually 3 days for the 3 days before, the 3 days after, which kills about 2 or 3 magnitudes worth of what you can see. But it's still valuable for the brighter objects, not the faint ones.
Okay. Yes, as Richard pointed out, Paul Gabor has been in the news. He's been quoted several times in the New York Times for the same interview, saying the same thing that he said once about 3 years ago. And every time there's another article on the leap second, they pull him back and re-quote him, saying, hey, if you're going to change whether the calendars and the clocks are connected to planet Earth, you may want to think about whether you really want to do that or not, because ordinary people do have a kind of connection to planet Earth. That being said, the politics of it really have very little to do with us and everything to do with the Russian GPS satellites. It's a long and complicated story that we could probably get him to talk about at some time. But who we've got tonight is one of my oldest and favoritist friends, Dan Britt. And Dan and I met each other nearly 30 years ago because at the time he was at the University of Arizona in the Lunar and Planetary Lab, and I would be hanging out there. And I think, though we kind of knew who each other were, it was a long walk back from LPL to our relative houses, which weren't that far away, where we just got to be talking about life, the universe, and everything. And Dan, you can pick it up from there. How much do you remember of that early conversation?
Well, I don't know. As old as I am, I'm lucky to remember I was in Arizona. Well, mostly one of the nice things about Arizona then was that there was a confluence of asteroid experts. And so you had enough asteroid people that every week you had a fairly well-attended asteroid lunch where we would talk about science, science politics, and current events, and almost anything else. And basically what Guy and I did was pick up from the asteroid lunch and talk about anything that came into our minds. The nice thing was that so little was known about asteroids at the time, you could spin any sort of yarn and it was halfway believable. And one of the things that caught our attention was that nobody had actually taken advantage of a lot of the data that was lying around, waiting to be taken. And a big chunk of low-hanging fruit was the physical properties of meteorites. Because as some of the leading lights at the asteroid lunch would earnestly tell me, there's nothing to be learned from meteorites. And that we were wasting our time in studying them. And of course, I listened carefully to the elders of my my profession, And I expect them, the younger people, to give me the same deference, which is I listen politely and then ignore what they say and go off and do what I think is right. And I urge, and I'm a professor at University of Central Florida now, and when I talk to students, I point out that listen carefully to what your elders say, and then do what you think is right, because your elders are probably wrong. And it turned out
how did you wind up being interested in asteroids and meteorites in the first place?
Well, strange story.
Make it as long as you want.
Okay. Well, I actually had a real profession. I was an economist working for Boeing. And I had an early midlife crisis when I turned 30 and decided I was bored with what I was doing, and I wanted to go explore the solar system because exploring the solar system was more interesting. And I decided what I wanted to do was get on NASA missions and be a member of the science team, because I'd seen Carl Sagan on TV and he was a member of science team. I wanted to do that. So I looked at what the specialties were on NASA science missions. And they were mostly physicists with a smattering of atmospheric scientists and chemists and geologists. And I thought, well, there's too much math and physics. And chemistry, I'd have to spell things that I can't spell. So I'll become a geologist. And that's literally how I decided on geology. And so I got a bachelor's, master's, and Ph.D. in geology and started chasing missions.
So where did you do that work? Where did you do your studies? You were at Boeing,
Well,
so I assume you were up in Washington?
Yeah, I was in Seattle, so I went back to the University of Washington, got an undergraduate degree in geology. And then I was lucky enough to get into Brown and got a master's and Ph.D. in Brown. And when I got there, I decided that I wanted to study asteroids because they were easier to get to. Because I noticed that if you wanted to do outer planets, it would take decades for these missions. And I was already in my mid-30s. So I wanted something with short travel times. So, and rocky.
You must have been what, the oldest student there at Brown?
Yeah, I was almost as old as some of the professors there. I was the oldest graduate. The day I arrived, I was the oldest graduate student at Brown University. And I've told Guy this story, but I was.
You know, I'm setting you up to tell this story.
Yes, I ended up, the first class I had, I ended up sitting next to the guy who's the second oldest graduate student. I was 35, he was 34, and he was from China. And I said, 34 is pretty old for a Chinese graduate student. And he said, well, yeah, I went to undergraduate at the regular time. But then the Cultural Revolution hit, the university was shut down. And at the end of the Cultural Revolution, they sent me into exile in Tibet for 9 years. And I said, wow, that's a really good excuse. Then he looked at me and said, what's your excuse? Which I just didn't have as good of a comeback. Anyway, so I postdoced at Arizona and met Guy. And we started talking about some of the low-hanging fruit in asteroids. And
well, okay, first of all, before we go there, tell us about the work you did at Brown. Who were you working with? What was your research topic?
Well, I was working for the best of all possible advisors, Carly Peters. And the way you know that Carly's mad at you is that she doesn't smile at you as often as she usually does. And so I got to work on a range of things that included looking at some of the spectral and physical properties of asteroids, how asteroids and meteorites relate to each other in terms of remote sensing. And I actually started speaking heresy at an early age, because what I found was that the spectrum of meteorites and the spectrum of asteroids don't align. that there's clearly something going on asteroids that makes them look different from meteorites. And when I first suggested this idea, I just got my head taken off by, again, some of the gray-bearded elders of our profession. And I had, even as a graduate student, I ended up having to push back pretty hard on some of these guys that, well, you know, that's your opinion, but the data says something else. And although I have the great respect for you, I'm going to go with the data rather than your opinion. And if you can come up with some data, I'd like to hear it.
One of the things that really impressed me in the work you did was to point out everybody knows that meteorites come in two types. There's the gray ones that are ordinary chondrites and the black ones that are full of carbon, called carbonaceous meteorites.
Yeah.
And what are the darkest meteorites you ever saw?
Well, the carbonaceous ones are the darkest, but a certain percentage of the ordinary chondrites are blackened, shock blackened. And so I wrote a couple of papers on shock blackened. And what the important thing I learned about then was that meteorites tend to be kept in really nice places. So the best troves of meteorites are in the capitals of what used to be continent-spanning empires, because meteorites fall at random, and so you have a better chance of picking them up if you have lots of territory. And so I dreamed up research projects that would force me to travel to these places where there are lots of meteorites. Like
Name three.
New York, Washington, D.C., London, Paris, Vienna. And so
Life
I had
is
a
tough.
wonderful time there. Yes.
I should mention that Carly Peters, your advisor, was a grad student when I was an undergrad at MIT.
Yeah, well.
And you're older than I am, so you were probably not that far from her age.
So true. And I'm feeling it now. So, but it hasn't.
Okay, you've got this background in spectroscopy, in laboratory work with meteorites, and an interest in asteroids. So you get a postdoc at the Lunar Lab connected to what?
Well, what I had done was I applied for a planetary astronomy fellowship, postdoc fellowship, with a strange guy named Larry Lebofsky, on the idea that, well, now that I've done laboratory spectra of meteorites, I should actually learn how to use a telescope. And literally, I had never used a telescope before Larry took me to the IRTF. So the very first telescope
it's the infrared telescope in Hawaii.
Yes, the very first telescope I used was a 3-meter telescope. And learned how to do spectroscopy of asteroids, and learned how hard it was. And I've mostly retreated back into the laboratory since then, but I worked for Larry for a while, and then I was able to get on my first NASA mission, which was Mars Pathfinder, which had absolutely nothing to do with anything that I had done before.
And what did you do for Mars? Mars Pathfinder, the folks here may remember, was in the 90s, and it was the first mission back to Mars that worked, that landed, since Viking. So it was almost a 20-year gap. What was your role in that mission?
I had been involved in writing the proposal for a camera for Mars Pathfinder, because the way NASA worked then was you had a committee of big names that would decide what should go on this mission, and they listed out a series of experiments they were going to compete. And of course, the guys who were on the committee wrote the competition rules so that they could go and provide the instruments themselves. And several of people on that committee were competing to provide the camera. And it just happened that we were able to skunked them all by providing a cheaper, better alternative than any of the rest of these guys could do.
How were you able to do that? How did you know that?
Well, we cheated. What we did was I was involved with a guy named Peter Smith, and he was the project manager of a lander that was going to Titan. And it was a very complicated optical instrument with really high tolerances. And so basically he was going to take the electronics and that had already been developed for this, and the chips and the imaging and basically all the guts of the camera. And they had such high tolerances that they had to throw away something like 95% of the hardware they bought and tested. And so essentially we took the refuge pile from this other instrument and used it for the core of the camera. And it turns out that half the cost of the camera is in that kind of stuff. And we had it for free. So we were able to add on a bunch of bells and whistles that our opposition could not afford, simply because we had dumpster dive for most of the camera.
This is a theme that I have found working with you over the years, that someone will come to you. Yeah, but someone will come to you with an impossible task, and you'll say, I have no idea how to do that, but I know somebody who knows something, who's got something parked in the back of their lab that they haven't used, which is exactly the thing you need.
Right. And that's how we actually started out doing
you and I.
Physical properties. Is I was able to dumpster dive for a pycnometer, which is the thing that measures the porosity of meteorites. And it was a nightmare to use, but we actually got some good data.
And you were able to. Yeah, we got enough data that you were able to then go to NASA and say, look, this is important. Give me the money to buy a commercial one that'll do it better.
Yeah. And we did that, and got several other people involved, including Bob Mackey, who did his PhD on that. And this is fast forward. I was by then in Central Florida, and I distinctly remember Bob, first day he was in my office, he said, what am I going to find in this project? And I said, I don't know, but I will guarantee you'll find something, because it's all low-hanging fruit and nobody has bothered to pluck it off the tree. And he actually found several useful things, and nobody who does an asteroid mission today does that without a density expert. And it generally is Bob, because nobody trusts me, which is okay. Well, actually a few people. I'm on the Lucy mission, for instance.
Right.
And
well, you've also been on the Deep Space One mission, which was a mission to a comet.
Right.
So we got a question here. Well, one person wanted to know about whether asteroids really are just collections of meteorites. If you can give a short answer to that.
Sure. Asteroids, most asteroids are probably piles of shattered rubble. And so the meteorites are basically come from mostly the interiors of these asteroids. A few of them actually come from the surface material. And we can see that because some of these meteorites have solar wind and planet gases in the structure of the meteorite. And the only way to get solar wind is beyond the surface. Comets, asteroids and comets are really a continuum of the same thing, in my humble opinion, because the only difference between rock and water ice is temperature, because water ice essentially can be a rock if it's cold enough. And this is, you just have to look at the tectonics on Pluto to realize that you can have mountain building and tectonics using ices. And so what you're seeing in comets is just a very cold version and later accreting version of what you see in asteroids. And so there's a whole continuum that was really fixed in the first 20 or 30 million years of the solar system history, when things accreted, how they got hot, how they were processed, how they interacted with the forming planets. And you can apply the same kind of tools you use on asteroids to look at comets and realize that these things are mostly empty space, that they are very weak, very kind of stickily put together, and have all sorts of interesting things in them.
Yeah, can you give us a little bit of what you actually saw when you got to, what was it, Comet Wilt that you went to? Or
no, this was Borrelli.
Borrelli, I'm sorry. I get them confused.
Well, one of the things that I didn't appreciate, and it only dawned on me once I had taken a look at Borrelli, was we'd have very poor pictures of the surface of comets before then. We'd gone to a great deal of effort to go to Halley's Comet, and ended up with really crummy pictures because the people that were building the optical instruments made of what were fundamental mistakes. You know, they were working on the best information they had at the time, but the idea that comets are dirty snowballs and that they have lots and lots of ice. Well, ice is really reflective, so ice should be bright. A comet, you have to recognize that you're likely to have some place that is 70 or 80% reflective. And that actually came up during the discussions in Borrelli, because people were talking about setting the exposure times for 70% albedo and 3% albedo. And I basically said that, well, you guys never spent the winters in the Northeast, did you? And what happened in Providence and Boston, as you well know, is that snow falling in November is still around in March, except that it's accumulated all this dirt over the winter. And so it's no longer 70% reflective. It looks like dirt. And that's exactly what's going to happen with comets. And so they wasted a lot of their imagery in taking pictures of Halley, and most of them were overexposed. And we were lucky enough not to overexpose the ones we took. Underexposed, excuse me.
Right. Yeah.
We were lucky enough not to underexpose things at Borrelli. And what you could see were surface features. And remember that the comets are the most erosive things in the solar system. They basically are losing about 1 meter of surface area, a surface depth averaged over the whole object. And so you should expect erosive features. And these erosive features are what you would expect in erosive areas that are subject to the same sort of processes, say, in the Southwest. So what we saw were things like mesas and fractures and modeled terrain and all sorts of interesting geologic features. And when we got far better images from Rosetta of their target,
which nobody can pronounce the name of.
Yeah, which I did. I was trying to think if I wanted to make a fool of myself, but
I actually met one of the guys it's named for, and I can't pronounce his name. It was a couple of Ukrainians.
Right. And what you see is just this wild agglomeration of erosive processes that combine deposition with opening up fresh areas, with slope failures, with undermining, with all the sorts of things that produce stuff that are very, very reminiscent of what you see in the Southwest.
I know one of the themes of the work you've done is to apply what we actually know about geology to planetary surfaces, which sounds like an obvious thing to do, but our field is often very reluctant to do it. Now,
Well,
I'm leading you into a story.
Okay. I'm not sure if I remember the story, but
well,
I will point out that most people that do planetary science are astronomers. And although I have the greatest respect for astronomers, quite often they are pathetic when it comes to geomorphology, which is okay. I mean, it's not their field. And but remind me which story we're talking about.
So about 20 years ago, when we were both a little bit younger, and you had reached a certain level of prominence in the field, you were on a committee that got to choose who the referees would be for various programs, projects, spacecraft missions, proposals, etc. And there was one involving Mars that you managed to tick off the entire field because you got a bunch of your terrestrial geomorphology experts to be the referees.
Okay. I actually don't remember the story as well as you do, apparently.
Okay. Well, one of them was the wife of our meteorite friend at Rutgers.
Okay. Oh yeah. Who is, yeah, a great geologist.
And so do you remember any of the rest of that and how that
No, I
turned out?
don't. I don't.
Okay. Basically, they went in and surprised people by asking the kinds of questions that they'd never been asked before, but in retrospect was sort of obvious should have been asked.
Yeah. And I think that's one of the great things about planetary science is that it's very susceptible to cross feeds from other fields. And the low-hanging fruit quite often is where you take something that is standard procedure and everybody does it in, for instance, geology, and apply it to planetary science. And that's what we did with density and porosity.
Yep.
And we basically created a whole subfield where I think one of the, where we made up some terminology. So the terms macro and micro porosity are now pretty standard. And we basically made those up out of whole cloth. And I knew that we had actually accomplished something when I was at a planetary defense conference. And I had an Air Force colonel earnestly explain to me what macro porosity was.
Not knowing that you had invented it.
Yeah, well, that you and I had invented it, right. Well, I said, oh, that's really cool.
One other story that I do have to get to before we finally get to your current work, but this goes back to Mars Pathfinder. So people may not remember, Mars Pathfinder was the first one that had a little rover attached to it, a cute little rover, and that cute little rover was not the thing that you were involved in.
Correct.
You had the imager on the guy that sat still and told the cute little rover where to go. So we've got these first pictures from the surface of Mars, and what you're seeing is a bunch of rocks. And how can you keep the rocks straight and, you know, tell one rock from another as you're discussing among yourselves where you want to send the cute little rover? So how did the naming of the rocks come about?
Oh, exactly that. In order to keep these straight, we started naming these rocks and basically put up a big panorama in the science team room, and people would put little Post-it notes on the rocks with their names. And naming rocks was open to anyone. But we decided that the way to do this is to establish a few rules. It should be not a proper name. It should be easy to spell. And the standard for that is I'm a terrible speller. I should be able to spell it at the first try. and that it's not snide or demeaning or anything like that. And we ended up with a lot of cartoon characters.
How did that happen?
Well, the sleep deprivation is a powerful force. And that's what happens on science teams where you're operating literally 24 hours a day.
Are you embarrassed to tell the story about who got you to use those names?
Well, my youngest son called me up and asked me to name a rock after his teddy bear, which I did. And I named a bunch of rocks. I named one after my Uncle Fred, because his nickname was Spud, and so there's a Spud rock on Mars. And the first rock we named was called Barnacle Bill because it looked like it was kind of covered by barnacles. It was a vesicular basalt. And we kept on a kind of a theme of cartoon characters. My son also wanted me to name a rock Scooby-Doo. That was early on. And so we kept, since we had one Scooby-Doo character, we ended up with all the other Scooby-Doo characters having rocks. Since this is at JPL and JPL has a large staff of people who worry about things, they were worried that we would end up getting sued by Cartoon Network. It turns out they loved it. They thought it was wonderful and sent us all t-shirts. I still have the t-shirt. Because it was great. It turned out that nobody ever suggested a name for a Disney character, which we never consciously went down that road.
Didn't have to test that one.
No.
So speaking of names, tell us about the mission whose shirt you're wearing now with the fascinating name Lucy.
Lucy, well.
Unique among NASA names, it apparently is not an acronym.
No, it's not. It's referring to a fossil that was found in East Africa, which is one of the earliest hominoid fossils. And the idea behind Lucy is that we want to go look at the asteroids in the Trojan swarm around in the Lagrange points around Jupiter, with the idea that these are some of the earliest things that have survived the age of the solar system, and look at the really primitive stuff. And one of the characteristics of any sort of NASA mission proposal is you need a catchy name. And typically people have an acronym for something. But you don't need to do that. You just need to have a name that people can associate with positive feelings, and it's easy to remember and easy to spell. And so the last thing you want to do is have potentially negative connotations. And it turns out that if you want to propose a name for a mission proposal, typically the big aerospace companies that you partner with have teams of people that research that name. And we'll come back with all the positive or negative things that were ever associated with that. And they take that very seriously. So Lucy was one of these things that not only reminded people why we were doing this, but it was easy to remember and easy to associate with positive outcomes.
How did the fossil get named Lucy?
Now that I don't know.
You don't?
I don't. I should know that, but I don't.
Yes. Well, Bob Mackey, who is also on this mission, has told me the story.
Okay.
That when the geologists found the fossil, they had a tape player going, and the song being played in their headphones when they uncovered the fossil was Lucy in the Sky with Diamonds.
Oh, no kidding. All right,
so
that
that's
makes
how
sense.
that's how it connects back up with going to something in the sky.
Right. And that song is kind of is the theme song for our mission. And
so now you know why.
I know why. I didn't realize that. I knew we've had random fossil anthropologists associated with the mission, but I've never spent any time with them, so I didn't know. We'll see
And
more.
that's why Hal Evanson had a chance to meet Ringo Starr. Seriously.
Which he greatly appreciated.
Yes.
Yes.
And if you know Hal, he's about what, 6'6"?
Yeah, he's the planetary scientist that looks the most like an outlaw biker.
And apparently Ringo is about 5'6", and as those of us of a certain age are getting shorter every year.
Mm-hmm. Oh yeah.
So what's your job with Lucy? What do you do?
I run.
Well, first of all, describe a little more the mission. Are you going to bring stuff back? Are you going to go in orbit around anything? What are you going to do?
No, we're going to fly by. Well, as it stands now, we're going to fly by 11 asteroids, 7 of them in the Trojan swarms. We've just done 3 actually, because Dinkinesh was just practice, but we, instead of flying by one object, we got 3 in one go. Because it turned out that Dinkinesh had a moon, and not just a moon, but a contact binary moon. So
it's 2 moons touching each other.
Two moons touching each other, and I can start showing pictures of this if you like.
Actually, Bob is putting up the pictures in the chat. So
okay,
unless you've got something that's not out there yet.
Well, I can't show you something that's not out there because that okay. I cheat less in my old age. Anyway, I actually had a chance to be in mission control for this flyby, and I thought, well, you know, it's just an ordinary chondrite. It's not going to be very interesting. So I didn't go. And boy, was I wrong. This was you know, a 3 Sigma interesting asteroid. Because not only does it have a moon, but it has this binary moon. And if you look at it, and Bob is showing the press release, the original press release picture, and now the one with the binary moon. It's a very interesting system. And what I'm interested mostly in is the internal structure of asteroids and what is going to be the density and porosity. And we weren't going to get close enough, and it's too small to actually measurably deviate the spacecraft with its own gravitational field. So we didn't expect to get a system mass and any density data. But since it has a moon, it looks like we will get, since we can characterize the orbit, we will get the system mass. We will get an idea of its bulk density. We can start speculating on what its porosity is, what its internal structure is. And if you look at the big press release picture, you can see that it's kind of vaguely top-shaped, that it has an equatorial bulge, but it has a lot of structure, a lot of scallops, and a lot of craters, what look like scarps. It has geology. But even though it does have craters, it doesn't have a lot of craters. So the surface age is not that old relative to how it weathers itself and how the surface moves around. So I think we're looking at a relatively young surface, and a surface that refreshes itself by mass wasting. And what we probably have with the moons are things that are that were flung off due to rotational spin up from the original asteroid, and that has slowed the spin of the asteroid quite a bit since it shedded mass. And there's a big story there to tell. And so people are going around counting the craters and counting the boulders and pondering these things now.
Alexa, turn off the table light.
Okay.
So we're now at 10 minutes to the hour. I've got basically 5 more minutes before I have to run away. So if there are questions, feel free to type them into the chat. And while I'm looking for questions, I'll finish with one of my own. When does Lucy finally get to the Trojan asteroids? What year will that be, and how long is it going to spend out there?
Well, what Lucy is doing is we're saving the taxpayers a lot of money by stealing angular momentum from the Earth, because it's a long way to the Trojans. And basically, Lucy is looping through the asteroid belt right now, coming back to Earth, and we're going to do another Earth flyby in the end of 24. And that'll loop us back out to much farther, back into the asteroid belt. We'll fly by another asteroid called Donald Johanson. And then we get another boost and go into the Trojans. And we start doing Trojans in 26. Then we come back to Earth again, get another boost, change our trajectory a little bit, and do more Trojans in 2031 and 32. So we're going to be, when we're cruising through the Trojan swarm, we'll be doing rendezvous, or we'll be doing flybys fast and furious. So we'll do 4 in like 6 months in the first swing.
I'm doing the arithmetic and saying that you're going to be a bit past retirement age by the time of that second fly through.
Yes, this has been a major bone of contention with my institution, who didn't realize that they were signing up to keep their overhead rates fixed for decades. And I asked them, well, didn't you read the date on the contract? And anyway, but that's neither here nor there. Yes, what I'm doing is I'm working with Bob Mackey, and the idea is that Bob Mackey will do all the work for me in the future.
Kind of what I had him do when he came here. He's doing all the work for me now.
Yeah, well, of course, you know, it's science is a younger person's game, and I could, you know, he's much more willing to work hard and be sensible than I will be, and so that's fine. And right now, one of the big issues is that we really need to confront this whole idea of what is a rubble pile and what are the various grades of being rubbly. And this is probably as good of time to deal with that as any time, because we've got a lot more data now. One thing that appalled me was that there's been a lot of advances in radar observations of binary near-Earths. And so we have you and I wrote a paper 20 years ago about the bulk density of asteroids. And now we actually have a fair amount of real data. One of the characteristics of that paper is we threw out almost all the measurements that other people had made because they were non-physical. The error bars were just so huge. But now we have some actual fairly good data. And we need to revisit this whole idea and start talking about the various grades of being a rebel pile.
I remember when I first looked into this stuff, back working on icy moons and trying to figure out the densities of stuff in space. And I found a table in the, what that big compendium, the ephemerides,
right,
that was published every year. And they had a table of 50 asteroids, their sizes and their masses. And I thought, that's fantastic. We can use this to calculate densities. And the first one I calculated had a density of 2.5. And the second one had a density of 2.5. And the third one had a density of 2.5. And then I realized where they had come up with the masses, because nobody had ever measured the masses.
Right. They had just assumed.
And then there was the famous first flyby of an asteroid that got a mass, which the Galileo probe got.
Oh yeah, Matilda.
And there was, I think it was actually even before then, it was the one with the
Ida.
little Ida, right, Ida and Dactyl. And they published the density, which was a pretty darn good density. And the science paper compared it against the density of different types of meteorites.
Oh yes. And it turned
Which was
out
fine.
Yeah, but it turned out that they didn't actually measure any of those meteorites.
That none of those meteorites had really been measured.
Yeah.
That the paper they cited didn't have those numbers in it, and we knew because we'd been looking for those numbers.
Right. And that was one of the reasons why we were able to go off and start populating these numbers, was to have actual data to actually compare.
Right. And we wouldn't have to lie about it like the authors of that science paper did,
Yeah.
who we won't name. Well, at this point, I do have to be on my way. Boy, it's been fun chatting with you again. And I hope everybody else here has enjoyed the stories as much as I have. Some of them new to me, some of them old favorites. And meanwhile, everybody here, spread the word. This might be turned into a podcast if Bob can edit it. And meanwhile, we are wishing you all the best on all of your asteroids. And maybe you have a very merry asteroidal Christmas and a wonderful new year.
Thanks.
Thanks to everybody. And I've got to run because the community mass is happening right now. So bye-bye.
Okay.
Thank you.
Thank you.
Bye.
Pam, I owe you an email. If you're still there, no Pam's left.
Okay.
And Bob, I owe you an email that you're going to get soon. All right. Bye, everyone. Bye, Deacon.
Bye.
Joel. Goodbye.
Bye, Chris. Thank you so much. Great presentation.